Correlation and regression. Okay, so one of the main issues that we have when we talk about correlation is that a lot of people think that, well, correlation means that one variable causes another variable, and that's not true, right? Correlation is not causation. I'm sure you've heard that term before. Some of the well-known topics of correlation research might involve violent television games and violent, television programs. Create this childhood aggression or create aggressive children. Another one is increased risk of heart disease is related to having a type A personality, right? So if you have a type A personality, you're going to drop dead of a heart attack. IQ is related to GPA, right? The higher your IQ, well, then higher the GPA. Stress is related to poor health, and exercise is kind of a one that's a little bit what's going around a couple years ago. Exercise is related to decreased depression. So the more you exercise, or if you start exercising, then you won't be depressed anymore. And we're going to talk about these a little bit deeper. We kind of start thinking about, well, are you sure that one causes the other, or are they just more related? Okay, and that's the whole point of correlations. Correlations look for relationships, right? It's trying to measure and describe a relationship between two variables, right? The depression and exercise, or the stress and the heart disease and poor health. Some of the things that, some of the characteristics that relationships might take a look at is the form, right, where the data points tend to cluster around a scatter point. And linear is the most common, but there's other forms it can take. Magnitude of the relationship, right, how strong is that relationship between one variable and the other variable. And then the direction. A positive sign describes the variables. They increase together, right, as one goes up, the other one goes up. The other one is more of an inverse or negative sign. As one increases, the other one goes down. Okay, so this is an example of a positive relationship. As the temperature goes higher, right, here's the temperature here, beer cells or cold drink cells goes up, right? So the more cold drinks are sold, as the hotter the temperature, so it's a positive increase. Negative relationship is as the temperature goes down, right, as the temperature goes up, the amount of coffee or hot drinks goes down. So as X increases, Y decreases. Okay, here's some different strengths, right? Talking about the magnitude of a relationship. And over here, so let's go through them one by one. We'll go through A first. So in this one, you have that perfect linear relationship. It's perfectly negative, or it has an inverse relationship, right? So this number would be -1, right? So we're concerned about not only the number, but also the sign. And correlations go between -1 to 0 to +1. You're never going to get a 2 or a 3 for your R, and that's your Pearson's R, and we'll get to that in a second. Okay, take a look at the next one. B, there really is no relationship here, right? The points are scattered all over the place. It looks like a chocolate chip cookie. With C, that's a pretty tight relationship, actually. I would say about 0.85 or 0.90. You can see here that the data points are tightly clustered around this upward moving relationship. Whereas with D, it's down, right? It's kind of pointing down there, but it's a lot looser, so around -0.4. So again, you're looking for the sign, is it positive or negative? And you're looking for the number, the magnitude, how strong are those linear relationships? Okay, some of the misinterpretations that can happen is one, causation, right? Assumption that a correlation or relationship between two variables is causal rather than relational. That just because the temperature starts increasing and increasing and increasing doesn't necessarily mean that that's causing the hot drink sales to go down. Because if that was true, well then I could just drop the temperature to negative, and it would the sales would be through the roof, and then if the hotter and hotter I got, then no coffee sales would happen. Well, people still buy coffee in August, even in Phoenix, right? Okay, directionality, inference made with respect to directionality, right? So again, if we increase one variable as X variable, Y will also increase. That's not always the case. Okay, going back to our first several examples there. Correlation does not prove that violent television or violent video games causes childhood aggression, right? Other factors, such as socioeconomic status, right? How wealthy or how impoverished, or what's the economic status of the child playing that game? Learned behavior, right? Is it more so that they're learning the behavior to be aggressive from parents and siblings and friends, or is it from the video game, right? And also just personality factors. Certain personalities are attracted to, seek out violent media, and others don't. Correlation does not necessarily prove that having a type A personality leads to heart disease. Other factors also play a part, right? So diet, exercise, and most importantly, this genetic predisposition play a role in who gets coronary heart disease. The next one, high IQ does not always result in high GPA. I'm sure you know people that have really high IQs and they are not living up to their potential, we'll say it that way, right? So they don't get straight A's in college, or if they didn't get straight A's in high school, right? A high IQ helps, right, you to understand the material, but there's other things that go into having a GPA, right? Showing up to class, doing your homework, working with others if it's going to be like a group assignment, those types of stuff. Poor health is not only the result of stress, right? Your exposure to different viruses and bacteria, how much sleep you're getting, all that contributes to your stress and your health level. The last one, depression is not always improved with exercise, right? What's happening here is they take surveys and they say, how often do you work out? And people that work out, 3, 4, 5, 7 times a week have lower rates of depression. Now, that's not to say that the exercise is curing the depression. What's happening is it's a comorbid factor going on here. So, right, so one of the side effects of being depressed for a lot of people is they don't want to get up out of bed. It's just too hard to get up out of bed. They have higher incidence of calling in sick, lower incidences of exercising. Right? So again, this exercising is not necessarily curing the depression. Right? So our symbol for correlation, right? So we've gone through Z and T and F for ANOVA. Now we're going to go through R for correlation. Okay? And R is going to help us measure that degree and the direction that those relationships between the two variables have. And again, a perfect linear relationship is notated as either a plus or negative, or positive or negative 1. And every change in one variable has a corresponding change in the other variable. So every change in X has a corresponding change in Y. So here's our formula for our Pearson's R, right? And so what you're trying, the numerator is the ratio, right? The SP is the ratio comparing the covariability of X and Y. Whereas the denominator, this sum of, or square root of, sum of squares for X times sum of squares for Y, is the variability of X and Y separately. So one is all them together, the numerator is them together, and the bottom, the denominator one, is them separately. Okay, here's a couple different formulas. This one up top here is just a definitional formula. This one down here is one we're actually going to use, right, to find our SP. And do take note, this is basically the sum of squares formula. It looks a little bit different, right? Instead of sum of X minus sum of X squared, that kind of stuff. This is a little bit different. Okay, so really quick, learning check. A scatter plot shows a set of data points that are clustered loosely around a line that slopes down to the right. Which of the following values would be closest to the correlation for these data? And data again is plural. So two words here, loosely and clustered down, or loosely clustered around, right? And then it slopes down to the right. So D is going to be all right. Anything that's going to slope down is always going to be a negative correlation, and loosely is going to be like 0.3, 0.4, that kind of stuff. Now if it said slopes clustered tightly around a line, that would be closer to negative 0.75. What about this one? A Pearson R of plus or minus 0 signifies a perfect linear relationship? Absolutely not, right? 0, Pearson's R of 0, signifies no relationship. Think back to that chocolate chip cookie, right, where this the data points are scattered kind of all over the place. What about this one? A negative sign in front of the Pearson's R signifies an inverse relationship. Absolutely, right? As the x variable increases, the y variable decreases, and it's going to create what we call an inverse relationship versus a positive relationship. Okay. Why we use correlation research, right? Prediction, right? Now, while again, it's not causing anything, most humans act in a very predictable manner, right? So we can use one known variable to help us predict another variable. Now, sometimes is this off? Absolutely. All right, validity. To help demonstrate that the assessment that we've already done truly does measure what it's meant to measure, right? The researcher designed the study to measure this. We can use Pearson's correlation research analysis to verify and to substantiate that validity. Same thing with reliability. This assures that an assessment produces consistent results. Okay? And also theory verification, right? To predict these certain tests that we may be able to run. Right? How we interpret correlations. Again, correlation does not mean causation, right? But the value of a correlation is affected by the range of scores in that data, right? And one of the scores that really affects the data is extreme points, or what we call outliers, and these have a huge impact on the Pearson's R. Okay. Correlation cannot be interpreted as a proportion, so we have to square the correlation, right? So after we're all done and we find the R, the Pearson's R, then we square it to find the proportion, how much that one variable is impacting the other variable. Okay. And this R squared is called the coefficient of determination. And again, it helps to measure that proportion of variability in one variable, x, that can be determined from the relationship of the other variable, y. So here we have a full range of x values, and it shows a strong positive correlation, like 0.3 or 0.35. But sometimes we look at restricted ranges, right? So here's our entire range of data points. And sometimes we're just going to look at a restricted range right here in this blue circle. Okay? And you think, well, why would we do that? Well, because of outliers. So up here in the top left-hand corner, we have a scatter plot here. We have the different data points, right? And you see how most of the data points are kind of clustered around 2s and 4s and 6s. And then we have one person way out here, right? And what we call this little blue dot is an outlier. And what's happening is, see how much of a strong correlation this produces with this outlier? Mm-hmm. But if you look at a restricted view, there's really no correlation. Okay? So think of a really, really rich person, think like Warren Buffett or Bill Gates or someone like that. I mean, like billionaire. Okay? And if he was enrolled in our class, I would say, I'm trying to see if there's a relationship, a correlation between enrolling in my statistics class and the wealth, your socioeconomic status, or your how much are you worth. Well, if Bill Gates or Warren Buffett is sitting in our class, wow, right? He's going to pull because his wealth is so much higher than everybody else in the class. He would say, yeah, there's a strong correlation between how much money you earn and if you take my stats class. But that's not really accurate. It's truthful, but not an accurate representation of what's happening to most people. If we throw out that outlier and get rid of that, one up here, we kind of see that there really is no correlation between how much money you're worth and enrolling in my stats class. So sometimes it's ethical, justifiable, good, right, to pull out those outliers. Okay. So Pearson correlation is usually computed for sample data, but again, we're trying to test relationships to find out what that really means in greater population. And the population correlation is symbolized by the Greek letter rho, and it kind of looks like a slanted P, right? So in our hypothesis pairs, if it's non-directional or a two-tailed test, our null hypothesis equals rho is 0, right? An alternative hypothesis rho does not equal 0. And if it's directional or a one-tailed test, well then rho is, less than or greater than whatever you're trying to find out which direction it's going in, 0. And then the alternative hypothesis is the opposite, that rho is greater than or again less than 0. Okay, degrees of freedom. Because we're dealing with two different variables, our degrees of freedom is whatever our sample size is, n minus 2. And you can look at your table B6. It should have like an R or Pearson's R up top there. And you can find your critical region, right? So again, how we did it with like Z crit versus Z obtained, and T crit versus T obtained, and F crit versus F obtained. Same thing, we're going to go R crit, versus R obtained. And the same rules apply there. We're going to try to see if we can reject the null hypothesis as long as our R obtained is beyond that critical region, because that's the value that's obtained. Very unlikely from chance alone that something else is going on there. Okay, let's get into our sample. Okay, so we have how many students? We have 1, 2, 3, 4, 5, 6, so 7 students. And we're going to say, what's the relationship between how many hours they study a week and their GPA? So in the X column, in the X category, we have their hours of studies per week. And then in the Y category, we have their GPA on a 4-point scale. Okay. So don't freak out. This isn't as bad as it looks. Okay, so we have, again, our students here. And we have our hours of studies here. When we square each one, right, because that gets rid of our differences if we ever have any negative numbers. I know time is not a variable that you can have negative on yet, but maybe if we're doing like bank account statements or whatever, weight loss, then it would be a negative number. So we're going to square each one of the x's, right? So 40 becomes 1600, 30 becomes 900, and then we're going to do the exact same thing over here for the y-axis. So this GPA of 3.75 becomes 14.06, 3.00 becomes 9.00, and you're going to do that for each one of the y's. You're going to square each one of the y's. Okay? Then at the far right, we're going to have x times y. Be careful to only multiply, like in this case, 40 times 3.75 equals 150. 30 times 3 equals 90. Right? So xy is just the x, not the x squared, times the y. Okay. Then we're going to sum each one of them. So over here, for sum of x, we just add up all the x's. For sum of x squared, again, we just add up all the x squared whenever we square that wrong number. Same thing for y, y squared, and sum of x times y. We're just adding them up. So let's find our SP, and again, SP equals sum of x times y minus sum of x times sum of y divided by n. Okay. So we have, again, we have x times y, right, 491, we just put that right there, minus sum of x, 160, times sum of y, 19, divided by our sample size of 7. Okay, this is going to get our numerator for r. Sum of squares for the x, right, is sum of x squared minus sum of x squared divided by n. So again, this is the classic sum of squares formula that we've been doing now for a couple months. So that gives us 1042. Now you are going to do that again for y. So sum of squares y equals sum of squares y equals sum of y squared minus sum of y squared divided by n, and that's going to give me 3.11. So now I have my bits I need for my denominator part of the r. Now let's just do some math, right? So we got 56.96 on the numerator divided by the square root of 1042.86 times 3.18 gives me a Pearson's r of 0.99. I then square it, right? So I take 0.99. Let's look at the critical values of r first. So get out your B6 table. And so we have 5 degrees of freedom, right, because n minus 2, with an alpha set at 0.05 two-tail. We can find the critical value for r is 0.754. Our 0.99 is definitely higher than our 0.754 critical value, right? So we can reject the null hypothesis. Hours of study per week does have a relationship with your GPA, right? So the APA statement then would be the researcher ran a Pearson's R study and found the test statistic at positive 0.99. They had 7 people in their study with a p-value less than 0.05, which indicates a reject the null hypothesis with alpha set at 0.05 tail. And then we square this 0.99, so take 0.99 times 0.99, and that gives us a coefficient of determination of 0.9801, which suggests that this variability between how high the person's GPA score is and the number of hours a week they study is 98.01% of that equation, right? If you want to think of it like that. Now, that does mean that 2% is something totally different. Maybe it's the classes they took, maybe it was the professors they had, maybe it was, all these other different variables that could happen. But 98% of the reason they have that high GPA can be traced back to or has a relationship with how many hours they studied. Okay. The Pearson relation measures a linear relationship between 2 variables, and the line through the data makes that relationship easier to see. Sometimes that scattering of all the different dots is hard to see, so drawing a line, a best fit line, directly through all that data helps us recognize, the relationship a little bit easier. And regression allows us to make predictions. This is what is huge about regression, is the predictability aspect of it, right? So what's the likelihood of receiving a speeding ticket on Dobson Road tomorrow at 7 p.m.? When you start asking questions like, well, how many tickets are given each day? What times are those tickets given away? Is there a correlation, a stronger correlation or a stronger relationship between the time of day and the number of tickets given at that intersection? Maybe they have, 3 police officers that are have jurisdiction over that intersection. And the morning police officer really doesn't offer a lot of tickets at all. But that night police officer, he is on it. I mean, you go one mile over the speed limit and you get a ticket, right? So again, it's not you speeding that's giving you the ticket. It's that person who's issuing the tickets at that time making that judgment call of saying, yes, you need to have a ticket. So regression and correlation are really closely related, right? They both look at relationships between 2 variables, x and y, and they use the same basic set of data, right? Paired scores. Okay. When conducting regression analysis, we're interested in both the magnitude and the direction of the relationship between those 2 variables, right? Because if it has a strong relationship, then I can make a pretty good prediction of whatever, my chances of getting a ticket or not getting a ticket. If it's a weak relationship or a weak correlation, then my ability to accurately predict if I'm going to get a ticket or not goes down. Okay. So here we have this best fitting line, right? So this linear relationship between 2 variables, in which relationship can be most accurately represented by a straight line. And if you've taken, Algebra 2, this is what you learn in Algebra 2, and all of you had to take it to get into this class. So this is looking at the relationship between the GPA, and maybe in high school, and their SAT score. Now again, you can have some people that aren't going to follow this regression analysis, but this is a best fitting line for most people. The equation for that best fitting line is y equals bx plus a, with x and y being the variables, and the a and b are more the fixed constants in that equation. Y hat, right? And that's exactly what it looks like. Y with a little hat on it is the predicted Y, right? Or what the researcher is willing to predict from that regression analysis for each value of the X. And Y minus Y hat is that error prediction, right? And regression minimizes that error, that total squared error probability. So again, Y hat equals BX plus A, right? And to find B, you just go SP, right? We just found SP, divided by sum of squares X, or R times SY divided by SX. Right? And A, right, the line that goes through M and X, right? So the mean of Y minus B times the mean of X. And again, to find the mean, you just take the sum of X or Y divided by N. Okay, so we're going to find regression for a set of 10 pairs of scores with a sum of squares for x equaling 17, a sum of squares for y equaling 12, our SP equals 13.5, our mean for our x variables equals 5, and our mean for our y variables equals 2.5. So we find B first, right? So B equals that SP, or 13.5, divided by sum of squares x, or 17. So B equals 0.79, and A equals the mean of y, 2.5, minus B, right? We already found B, the 0.79, times the mean of x, so 5. So our A equals negative 1.45. Okay, so what about this one? A linear regression has a B equaling 3 and A equaling 4. What's the predicted value for y, or sorry, predicted y, or y hat, for x equaling 7? So I'm going to go back up just a slide, use these equations right here. Okay, and then whenever you, so push still pause, and then whenever you get it, come on back and I'll show you the answer. Okay, so it's 25 as y hat equals b times x plus a, so 3 times 7 plus 4. Okay, how about this one? An assumption of regression is that the relationship between x and y follows a straight line. So do you think that's one of the assumptions of regression? It is. An assumption of regression is that that relationship between x variable and the y variable follows that straight line. That's what regression is versus correlation. Okay, so again, complete your homework. Call me or email me with any questions, and have fun with it. This is actually a pretty fun chapter.